Okay, so first of all, thank you for inviting me to give this webinar. And yeah, so I will continue. I'm Xavier Porte, and I'm working in as a postdoc in the group of Daniel. And I will continue a bit this talk about 3D printed waveguides. He has already explained all the integration for neural networks and the basis. So I will add a bit more information on a different direction we are exploring, which are these core-cladding structures. So yeah. So basically, yeah, I will. So as I understood a bit this webinar, I will explain a bit the basics, how we can and why to make these core-cladding structures, how we let's say decided to or yeah, the direction how to print them, characterization, and also to go a bit beyond simple waveguides, how we designed splitters, also single mode splitters, and based on the same principle. So yeah, as Daniel already introduced, this 3D printing based on direct laser writing is finding a lot of applications in photonics. And I highlight here too, like this photonic wire bonding, and besides the complex photonic networks that Daniel already explained. That actually is very interesting and is generating a lot of research because it gives this opportunity to make this free form and prototyping to hybridized platforms. For example, in telecommunications and silicon photonics, it is becoming very interesting to generate these photonic chips where actually you can, by 3D printing, make these flexible connections in the volume between a certain chip of one type and a certain second chip of a totally different type, where you can actually modify and optimize the connectivity between the two types of inputs. Here even a third one. So, and also for us is more interesting to generate these complex structures in the volume. Daniel already explained, and we have already published a couple of papers on that, and we are increasing our momentum in this direction. And what I will explain here is actually how we face the printing of structures that propagate single modes inside. And this is interesting. I mean, it's interesting in many fields of telecommunications and photonics, because actually you may be interested in the effects that require single mode propagation, like, I mean, that require interference or coherent communications, etc. So typically, optical fibers are used for that. And I will first introduce briefly very basics of optical fibers. So they are typically this core cladding made of silica structures. And here I show a step index. That means in the core, you have a certain refractive index, which is larger than the refractive index of the cladding. And then by total internal reflection, you get the light confined inside the fiber. And if we define this delta parameter, actually most single mode fibers are basically working this weak guidance approximation, where basically you have a very small difference of refractive index between the core and the cladding. So the mode is weakly confined, and the solutions of that type of structure is actually these linearly polarized modes, where this would be the fundamental mode, the one we are interested in a priori. And then, well, this is an orthogonal set of solutions. So you have all these different LP modes where the order is actually given by, so these are higher order modes, and basically their structure is defined by Bessel functions. Yeah, and we basically are interested in the conditions that will give us this fundamental propagation, fundamental mode propagating. So as a practical example, this 630 HP fiber that you can buy from Thor Labs, for example, you have these typical values of diameters core and cladding, and this kind of numerical aperture for the structure. And you see that the guidance parameter actually is very small. So that means the difference of internal and external core and cladding refractive indexes is of the order of a percent, smaller than percent. So when you basically want to find the conditions for the single mode propagation, you have to find what is in your parameters that confine this monomode regime. And so if we define this, you can find in basics of fiber optics, any book. So you have this normalized frequency that is a very useful parameter because it includes most of the parameters of the fiber. And when we basically plot this mode propagation versus the normalized frequency, which you can hear here, they are related by this dispersion relation, then you have this kind of plot where you basically find the conditions for the different modes to propagate inside the fiber. And in a cylindrical fiber, the condition for single mode propagation is to have a V between 0 and 2.4. So basically, this is the range for the single mode propagation in a normal fiber. So going to the paradigm of 3D printing and how to make fibers, let's say single mode waveguides in 3D printing. Basically, Daniel already explained the basics of direct laser writing. So the idea here is that you create these voxels by two-photon polymerization. You attack the resin with femtosecond laser. And actually, what we will explode here to make these complex structures with the core and the cladding is the fact that the refractive index of the resulting polymerized resin depends on the laser power. So there are different studies that demonstrate and study that in different resins. So for the resin we are using, which is this IPDIP, the highest resolution resin that provides the company Nanoscribe, which is the one that has the machine so we have the machine from Nanoscribe. So basically, then there is this study that shows that the two-photon polymerization is basically depending on the amount of laser power that you put for a given writing speed and for a given, let's say, resolution you want. You can change the laser power, so the exposure, the amount of energy per voxel, and you change the refractive index. So with this kind of quasi-linear dependence, we play to generate structures where we have a certain laser power in the core that is higher than the laser power that we put in cladding. And basically our approach is, so we can, as we cannot play arbitrarily with the laser power, because in fact, if you use a too low laser power, you may not have a totally polymerized structure, and therefore the structural properties are not optimal. And if you use a too high laser power, basically it can create a lot of defects. It burns the resin by overexposing it. So what we did is to find the two limits of the range where we can operate. And within this range, we choose a laser power for the cores that is on the high side and the laser power for the cladding that is on the low side. And we basically then decide to tune the diameter of the waveguide as a parameter where we will hope to find the condition for the single mode propagation. Okay, so here's an example of the type of structure, so microscope image, optical microscope image of the type of structure we print, which is actually a parallelepiped with a lot of waveguides inside, so 25 waveguides, where we tune the diameter, and then we will study the propagation as we inject light on one side. You would see in the optical setup, and basically we measure the output and we measure the mode at the output. So yeah, we scan the cylinder diameter, and also we print two types of waveguide, not only a step index where the refractive index in the core is constant, but also graded index structure where you actually have a dependence, a radial dependence of the refractive index, which for us translates in a radial dependence of the laser power exposure. of the energy exposure, laser power, and we choose this kind of parabolic dependence so that you can see here, basically in the step index, you have a certain laser power for the core and second laser power for the cladding. Meanwhile, in the graded index, we have this kind of this quadratic transition core cladding, and that is to demonstrate we can do this, but also because it's of interest, these graded index fibers are typically used for low mode fibers and in low mode fibers for low dispersion, for example. So we were interested to demonstrate and explore the two options. We see that typically the number of modes supported in same parameters for a graded index is lower, so they have a higher cutoff frequency. So basically you can go to higher diameters and still confine only one mode. So these are different properties we expect to find in our structures. So basically I show very briefly here the optical characterization setup sketch. So basically we illuminate with a laser. In this case it's a 660 nanometers. That's why I also show before the properties of a 630 HP fiber. So it's a 660 nanometer laser. We use LED to illuminate with white light and take these optical microscope images of the printed sample. We inject the laser light in the structure with a 50 times microscope objective, so that gives a very high, so we use a very high NA, so to excite as many modes possible in the waveguides, and then we basically observe the throughput of those waveguides, and this is just to align, so it's a second camera to align in reflection. So we use CMOS cameras just to take the image, and then we calculate the losses of the waveguides. So this is first characterization of such waveguides, and it's a lot of information included here. So basically we change the diameter, as I said before, and we calculate the throughput. So that means the integrated power on the waveguide. And I show here in blue the step index, and in red the graded index, and every set of points, red and the blue, correspond to a different cube with changing diameter. And what we see is that the losses, basically the confinement of the mode reduced, so the mode is more and more confined until it is guided. Here for the step index, already around 3.54 micrometers, we have the mode with, let's say it's plateau of losses, and in the graded index it starts later, and this is consistent with the information I gave you before for single mode fibers. And I show here 3 cuts because it's interesting to see the output of the modes, because I think it's quite clean and gives illustrative information. So here when we are still in one mode, so the fundamental mode propagating the 2 fibers, the step index and the graded index. In the second cut, we see that here there is this dip, and then poof, it shows that the second mode starts to enter for the step index, but not yet for the graded index. And then here I show a condition where actually we have even a higher order mode for the step index, and the graded index already is multi-mode, or let's say second mode entering. So with that, we can see basically these conditions are single mode for a step index, and in this range we have a single mode propagation for graded index. Losses are quite high, so not impressive at all for a photonic component, but it is good for our first approach. And actually, this amount of losses include everything: propagation losses and coupling losses, because we attack with a very large NA. But when we match the NA, we reduce the losses of the order of 1.5 dBs. And we wonder if actually this is from propagation losses. So to respond that, we basically printed the replicas of the same cube, but that originally had 300 micrometers height. And we printed six replicas of this cube. So from 50, 100, 150 to 150 and 300 micrometers height. And we measured these losses and how these losses changed with the height. And with that, we could determine in fact, the propagation losses. So by fitting these points in 2 different inputs correspond to single mode and to first mode, we basically fit the losses with respect to the length of the cube, and we find this 0.005 dBs per micrometer, which is I think is quite good. I mean, the quality of the printed structures is good. I would say this is a bit the limit of the polymer. So, and also this considering the original height of the cube, so proves that there is 1.5 micrometers, sorry, 1.5 dBs. We measured when matching DNA were actually the propagation losses. So we were basically good on that. And well, now I will shift to the second thing, which is how we approach the design and implementation of splitters in this core-cladding approach. So before Danny showed these complex structures where you have this, for example, these fractal trees and these Haar filters, but all these structures are air as a cladding, let's say. So they have the polymer waveguide, but in all these structures, when there is some splitting and coupling, it occurs in a multimode way, and actually the outputs we see that are multimode. And here we wanted to do splitters the same way, but with conserving the single mode. So what we decided is to print this same type of waveguides. We choose a diameter that fits the single mode propagation. And then what we decided is to do this tapering, this adiabatic tapering transition to split from 1 to n. So in this case, so we tried 2, 3, 4 outputs. And the idea is you come the single mode here, and the single mode basically evanescently escaping the central waveguide, and actually is accepted by the receiving. Then okay, so that is the approach we decided to follow. We printed such kind of structures where the central waveguide is adiabatically coupled to the side waveguides. And here I show an example of 1 to 4 splitter where the input is single mode, and actually we split it in 4 outputs which are also single mode, and the losses I show here. Actually, it's a bit more complex figure because this is the excess losses with respect to coupling to a waveguide of the same diameter, and for these 1 to 4 splitters. And here what I scan is a parameter which is this splitting separation. Okay, so because we were wondering if so what would be the effect of that separation between the outputs. Of course, it's correlated, I know, to the length and to the angle of this adiabatic, but this was our first approach. So here we just split it further and further the outputs, and so how the losses were going increasing linearly in the dB scale. So and the excess losses of the 1 to 4 splitters is actually rather very small, so around half dB. Just a very last detail on this adiabatic coupling and dependence on the distance. We basically scanned in long 300 micrometers waveguides that where we basically changed the distance between them. So to see how was this effect of the coupling to neighboring, to the evanescent coupling to neighboring waveguides. And basically we characterized this a priori expected exponential dependence of the separation. So actually this confirms our previous finding, and it also shows that if we rapidly separate the outputs after the coupling region, basically we will find an exponentially decreasing influence of the output. So the coupling, we can basically define and reduce the coupling to the desired coupling region in the adiabatic part. And with that, I arrive to my summary. So I hope, well, I hope you got into the idea of how we decided to create these core cladding structures. Basically, so first I explained a bit the basics of single mode propagation in optical fibers, how we decided to create the same conditions with 3D printing structures, how we characterize the conditions for single mode propagation, and finally an application would be we demonstrated single mode splitting in 1 to 4 couplers, for example. So with that, I finish. Thanks.